Hello, everyone connected already to the webinar. We will wait another minute or two for all the people trying to connect, and then we'll start right away. Make yourselves comfortable, please. So hello to everyone connected. I'm just saying again, we'll wait less than a minute for the last people to connect, and then we'll start. So hello again to everybody connected to this webinar, and thanks for joining us today. My name is Ronen Shecter. I'm CTO in Fluence Corporation, and I will be presenting today in this webinar. Reminder, our topic today is distributed water management using decentralized systems. I will present the concept, what I mean, provide some examples, a case study, and eventually show how some of the products Fluence has enabled this attitude of distributed planning in water management. Just a housekeeping note, during the webinars, you can communicate with our team. They are there and ask questions. They will reply directly to you. At the end of the presentation, I will also pick up some of the questions and discuss it here. Just a few words about us. Fluence is a global company providing water and wastewater solutions with operations in, I hope I don't forget any location, the US, Argentina and Brazil, Italy, Dubai and Egypt, Israel, and in China. And as I already mentioned, we in Fluence focus on excellence in decentralized solutions. So let's take a couple of minutes for context, the big picture. I'm guessing all of us are sitting in our homes or offices right now, where there's bathrooms and kitchens with running water, but actually more than half of the world's population does not have proper sanitation services, and more than a quarter does not have access to safe drinking water. And this is growing, as you see on this slide, the numbers. So narrowing these gaps in view of this global population growth is a major challenge for our industry. We must apply the most efficient means to close this gap. And as you might imagine, the topic of the presentation is what I'm claiming might help close this gap, bridge this gap, and achieve these goals. In the most developed economies in the world today, they're aiming for a circular economy. In our water business industry, this is associated with water reuse. There is also nutrient recovery, but the biggest resource available in wastewater is water itself. So closing the loop and having this entire cycles should eventually be available everywhere in the world, because this is not only about environmental conservation. It includes sanitation in the waste treatment, and it is also related to water supply through reuse. So there's several different growth and development directions we're seeing coming up, happening already, but in our future. On the left side, we see the symbols for urbanization driving growth and development in cities by adding neighborhoods or renewing existing neighborhoods. So this is one area of growth. The rural areas in many places are many times underdeveloped relative to the cities and towns, although they do cover a large part of the population. So matching their level of development is another growth area, another task. And we have the developing countries where water infrastructure is a major part on their path to development. And what is limiting development in many of these cases is the cost. The capital investment in infrastructure to provide wastewater treatment as well as water supply. As I see it, the task of engineering and technology in our market is to resolve these cost issues and enable sustainable growth in all of these different directions. So let's start by diving right into the concept description through an example. In this example, in this map, we're showing a region in South Spain. As you see, population about 80,000 people distributed over a large area in quite a few villages and two small towns. So along the description of two scenarios I want to show on this map, I will relate each component of the system, of the plant, to its capital cost and its operating cost, CapEx and OpEx. So start with the conventional approach, where there would be one big central plant. The plant is, of course, associated with an investment, but what some people are forgetting sometimes is that the collection system for the sewer network might cost 2 to 3 times the cost of the plant, and this is actually the major cost item in a centralized wastewater treatment plant. And if we're talking about the type of future we prefer, or I prefer, we would always have reuse as well, and that adds additional piping network for the reused water. So all of these are investment cost items, but there's also operating expenses associated with this plan. And this is the pumping. The pumping stations themselves are actually an additional capital investment. Pumping consumes energy, and there's an operating cost associated with this scenario. And then there's the operating and maintenance. Maintenance is an issue in long distance piping network, just discovering there is a leak, finding where it is, takes time and resources. It's not always as simple as finding your failure in a plant. So what's the alternative plan that could be compared to this? So for the same area, we could have many small plants treating the wastewater locally. This is associated with much shorter distance collection systems, just up to each of these plants. And similarly, the reused water supply would also be shorter, and we'd have local treatment and reuse. So there might be an advantage here in cost to offset the investment in many small plants instead of one big plant. Regarding operating, so of course, first of all, there are technologies out there like MAER-based Aspiral that I will present in more detail later on, that might match or even beat the energy consumption of conventional treatment plants. So that's one item that could be ruled out. And then there's much less pumping of wastewater and water, and the maintenance as well as the routine operation could have a customized structure such as mobile teams running around carrying standardized replacement parts to take care of any failure, which would be easier than looking for the failure along a system of piping. So just summarizing the differences, there's these two plans. They're different in many aspects, and just by visual impression, it is evident that the decentralized plan is definitely more flexible, as it could be installed gradually one by one, as opposed to a central plant that is essentially built all at once, and very sustainable for local treatment and reuse. So if we consider the type of plan, using small systems in many places, like in the picture shown at the top of the slide, we can look forward to a future of wastewater management, both treatment and reuse, with better performance in all parameters, with lower and gradual investment, with lower energy consumption, and an efficient operating and maintenance that is customized to handle this type of system. I gave the example for wastewater treatment, and I want to note that this approach also applies to water supply. The general idea is local treatment of local water sources, like wells, brackish water wells, seawater desalination, river water treatment, whatever is available locally. This way, you distribute your water sources, and they actually reduce the risk of failure of one system to influence your entire water supply. One of the benefits listed on the right is having less long-distance piping. There's also less possibility of non-revenue water associated with the losses, so actually higher efficiency with the distributed design. In some cases, another benefit might be lower environmental impact of brine discharge. So several small plants desalinating locally have a smaller brine discharge locally, so the discharge is already distributed, and you don't have a point source influencing the environment in one place. Just a note, this entire approach is very case specific. We're not saying this is the way everything should be done, and there is some balance between a decrease of decentralization to match the needs with some centralized systems, both in water supply and in wastewater treatment. So the entire concept, of course, does not only relate to developing countries. I mentioned urbanization before. So here's an example. A growing city can treat and reuse locally without loading the existing infrastructure for either a new neighborhood or a growing neighborhood. So it could have this local collection system leading to several treatment and reuse plants, as shown in the enlarged picture on the right. So that's the case for cities. Another case in the developed world might be aging infrastructure, that the replacement may be hard to finance and even difficult for the city life to bear. You turn the entire city upside down, digging out the old piping and putting in the new one. This is merely an idea, but local treatment and reuse might make more sense, at least in part, than a massive citywide repiping project. And there are actually some publications and university studies published promoting and quantifying this idea for specific cases. So what we are saying is that local treatment and reuse are beneficial and make sense in much more cases than they are considered today. This is a concept that is not your standard approach to water management. As a water professional, personally, it makes me think that this must be some kind of a temporary inefficiency in the way we work in planning. And this is why we are preaching to consider the distributed alternative. And we are not the only ones to say this. Just look at regulations in China and the Philippines. In China and the Philippines, same as far as I know, the regulations are pretty similar or the same for large plants and small plants. And China is massively going for installation of a very large quantity of decentralized plants. More than 100,000 administrative villages are going to get such a system installed within the last 5-year plan. The US EPA also guides and encourages to implement proper systems for the last 2 decades at least. Just look at the fact sheet from about 20 years ago. In Sydney Water, in Australia, they have a very unique initiative of sewer mining, where they are enabling entrepreneurs to extract water out of sewer pipes and sell it as a fee to the water utility. This is all decentralized and distributed treatment and reuse, just already happening since, I think, 2007 or 8. In the field of standardization, there's at least two ISO standards in writing dealing with decentralized and distributed planning. One is providing a tool to calculate and compare life cycle costs of different degrees of decentralization to select the optimal solution. And the other one is general guidelines for selection of decentralized and on-site wastewater treatment systems. So there too. There is actually quite a lot of university research and publications on this topic. I have just brought one of them at the bottom right side of the slide to show how they are demonstrating for one specific case that the cost for a distributed scenario might be almost half of the conventional centralized scenario. So you see the first column is scenario 1 centralized, and then they're looking at they're presenting here three different decentralized scenarios, and they can actually show the costs are always lower and might be even much lower. So just in view of this type of work, let's walk through one numerical example that we did. This is actually one based on my hometown, where it's a very small town, 2,000 people, and very hilly terrain. This is sort of the topography, and the general plan is that the sewer flows downhill. They have these 3 pumping stations, and the wastewater treatment plant there is pumping from the pumping station into a centralized plant located at a safe distance, like anyone would do if you read the literature from the last 100 years or so. And these are the numbers. So we have a total of 900 cubic meters per day in average, and the sewer mains are more than 4 kilometers in length. This is the larger diameter piping and 3 pumping stations. So these stations have this 6.5 kilowatts almost of power consumption average daily. The alternative to this plan would be the simple distributed plan instead of pumping stations. Just instead of them, you don't have pumping, you just have local treatment and either discharge to the environment or local reuse as required for agriculture nearby. So the capacity of each of these plants would be very similar. Take the total wastewater capacity. There's no main piping, there's no pumping station, so a lot of energy is saved there. And just for this very small example, the investment cost benefit would be more than $130,000 for the project, and over the lifetime of the project, it would be almost $500,000 for this very small town to bear. So that gives an idea of the sizes and the prices. Work based on this example was actually presented and published as part of the proceedings in WestTech 2019, and is available for download under the site as shown on the bottom right. The table and charts are actually taken from there. So we did the life cycle cost calculation per cubic meter, and we're seeing that there's more than 20% difference per cubic meter in the cost per between the completely distributed plan to the completely centralized plan, which is a big difference. Everyone will agree. So just entering the last lap of our webinar, I want to present shortly the smart products that Fluence proposes for the decentralized plan. On the left, there is the unique new technology of MAER, packaged as a standard Aspiral system for biological wastewater treatment. This is a line of products brand Aspiral that is all based on the new and innovative MAER technology that I will mention in my next slide. There is also the uniquely designed and also standardized NIROBOX line of products for filtration and desalination. So based on those building blocks, you can distribute your wastewater treatment and your water treatment system using standardized prefabricated building blocks. That's the general idea. Just a word about the MAER technology. Many already know this new principle. It is the new kid on the block, I think, in biological wastewater treatment. In a nutshell, as you see on the left side of the slide, it is based on a membrane. The membrane is a self-respiring membrane that also supports a biofilm. The biofilm is aerated by the membrane and treats the wastewater. So the MAER is this to remove total nitrogen using very low aeration energy. These Aspiral systems have already been chosen for more than 150 projects around the world, and yes, most are in China to date. Also note that the Global Water Intelligence magazine has listed MAER, as you can see on the bottom right side of the slide, as number 4 on the list of top 10 water inventions of the last decade. There you have it. A word about the Niro Boxes. These are standard, pre-designed and prefabricated desalination and filtration systems. The seawater desalination system, for example, on the left stacks 1,500 cubic meters per day capacity. As far as I know, this is the highest capacity per single 40-foot marine container available. So this just demonstrates that these are really neat and tight designs, that you get a lot act in a small volume, small footprint. So, ladies and gentlemen, this pretty much concludes my presentation for today. I hope this was interesting and maybe even inspiring thoughts on distributed networks of decentralized systems. For more information on our systems and for collaborations on decentralized design or projects, you can contact us through our website. By the way, on the website, you can try out our design Fluence tool for the preliminary design of your application. I think that some of the questions were already answered by the team members during my presentation, but I will pick up a few over the last few minutes here. So there's one question asking why is it important to remove nutrients in small plants? This is actually a valid question. Different requirements for small plants vary widely between different countries. And we see places where there's no nutrients requirements, and we see places where they are as demanding as from large plants. So the important thing is that you have the technology to enable nutrients removal to any level required, and then you just provide what is required. Of course, you don't do unnecessary work. So the reason it is important to remove nutrients in small plants is that in some places it is required, and it is important that you have the technology to provide it where it is required. Another question is whether Fluence ever actually implemented decentralized wastewater management. So luckily, we're in a way already there. We did set, of course, a lot of decentralized systems, but in one specific case that I want to mention is in China through one of our partners, ITEST. They actually install and operate all of the wastewater treatment systems along a highway. So there's a long highway, and on both sides of the highway, every few tens of kilometers, there's a station, people stopping, restaurants, gas stations, and each one of these has a wastewater treatment plant, and there's one company handling all of these systems. So this is one of the best examples I have today of one entity installing and operating a multiplicity of systems as one treatment plant. Any other? I'm just looking, trying to understand the question. Okay, so there's one question here saying what are the target parameters for MAER? So I'm not 100% clear on what that means, but I want to note, relating to this question that could be understood in more than one way, that effluent quality obtained by MAER is very much a matter of design. So actually, a building block, like I said, there's quite a few different models for the Aspiral MAER biological wastewater treatment plant. It could be designed with a higher load or lower load, and a couple other parameters to produce higher or lower quality effluent, and that also influences, together with temperature and other parameters, the HRT or the size to meet a certain specification. And I hope this answered in part, but in any case, of course, we can handle any specific request gladly. There's a repeating question here that I have seen regarding the life expectancy of the membrane. I'm trying to find the other one. This has been asked more than one time, so I want to say a word about it. Yeah, so life expectancy is long, and it is longer than any of the systems we have installed. It is expected to be more than 20 years for sure. The question is how much more. In any case, Fluence provides 15-year prorated product guarantee for the MAER membrane to provide confidence in its life expectancy. Better jumping here. Let me pick another one. In any case, I'm just noting here while I'm browsing through the questions that all of the questions will be answered for sure. We will correspond with you and make sure that you got your answer and that you are satisfied, or if there is any follow-up on it, we are glad to do that. Okay, so there's a question here that just about the topic I like, that asks if Fluence has ever installed a system, an Aspiral system powered by solar, off-grid, or among any of its. It's not 150, it's actually more than that, I think, more than 160, but never mind. So have we ever done that? And the answer is no. We know that we can design the system for an almost constant energy requirement throughout the day, which would be low. We did, low, and we did look into it with sort of a research grant, but it never went through, so we did not actually install any of these that are completely off-grid. Would be very interesting for me and for our company to try out this concept that also demonstrates the advantage of low energy consumption. So there is another question here about, can MAER address DNR and how? So yes, of course, the main and biggest advantage and differentiation of MAER to any other treatment technology is its ability to remove nitrogen. It actually performs simultaneous nitrification and denitrification throughout the process. This is very unique to MAER, where you actually hold an aerobic autotrophic biofilm on the membrane performing nitrification just beside the anoxic mixed liquor that performs the denitrification in the same volume. So this is very unique and special for MAER. It can relate into another question, maybe even by the same person, I think. It can reach as low as 5 milligrams total nitrogen easy. We've done that. I am sure we were never actually requested to comply with much lower requirements, but I'm sure we can design for that as well. And this is regarding nitrogen, but we've also demonstrated biological phosphorus removal with more than 90% removal through the MAER also, so that is also achievable and relates to nutrient removal. What others are they? Okay, so there's one question here about the wastewater collection to the decentralized facilities. So I wanted to just clarify something that was presented earlier in this webinar, and that there are, I categorize the collection system to two main parts. One of them is the gravity flow piping, and the second is the sewer main. So there's just a certain distance you can go by gravity, and then you reach the pumping station or lift station, from where it's a completely different story, usually higher flows, and this is the more expensive part of the piping. So the gravity flow needs to be installed, the piping needs to be installed. The parts that you actually save and don't need is the main that go all the way from the pumping station to the main plant, and this is the longer distance and larger diameter piping that is responsible for most of the cost, or the piping cost. I am aware that even the gravity sewer is a significant cost in places where it does not exist, and in such cases, there's other solutions that were not presented here today. These are on-site systems that are coming out soon based on the same technology. And if you stay tuned, you will hear about that too, and there will not be any piping in that case. Okay, so I think that there are a few last questions remaining unanswered, either by me here or by our team responding in writing. Everything will be answered, and I thank you again for joining us today. It was a pleasure to share our ideas, concepts, and products with all of you, and I hope we meet the market. Thank you.